In this chapter, we're going to be talking about multiple linear regression. So if you remember from simple linear regression, simple is where we have just one predictor. So multiple, the only change here is that we're going to allow two or more predictors, and we're going to be fitting that relationship in the form of a linear equation, which for our purposes at this point just means that we're looking at a like fitting with just a linear term. So at this point, we're not going to be doing anything with a curved relationship, even though you still could do that and you could still call it a linear model or linear regression. But we're just going to focus on the more obvious application where we just have linear relationships between predictors and a response. So I loaded some data here. It's cereal information. So I have 77 different cereals and just some nutrition facts about those cereals. So the number of calories, as well as sugar, carbohydrates, protein, other things like that. And so what we're going to do is let calories be our response variables. We're going to try to predict slash model number of calories in a particular cereal based on other nutrition information. So, for example, how does knowing the sugar content or the carbohydrate content give us indication of what the calorie content might be? So I'm going to start. I think I've already loaded these to begin with, but yeah, these are all loaded. I'll be using these three packages throughout this video. The code is really not important in this video. I just want you to focus on conceptually what we're doing. So let's start by just looking at a simple linear fit where we use sugars as a predictor of calories. You can see here that on average, as sugar content increases, calorie content is also increasing. Now, granted, there are certainly exceptions to this, like there's some kind of low sugar cereals that have relatively high calorie content and vice versa. But we do see some bit of a relationship where knowing sugar does give us a slightly better indication of calorie content. And sure enough, if I build a model where I kind of look at this, I do get an R squared around 31.82%. So we're explaining about almost 32% of the variability in calorie count by knowing the sugar content. I could also look at carbohydrates as a predictor here. So let's go ahead and do that. So we're going to build that model here as soon as R lets me. It's kind of slowing down a little bit here. Here we go. And so carbohydrates doesn't seem to be as strong a predictor. In fact, there's a lot of kind of unusual data points. So I have some low carbohydrate cereals down here. And then in general, though, the relationship is just not as strong. Like a lot of this data looks very similar across the board. And sure enough, if I do a linear model with carbohydrates, my R squared is only around 6%. So I'm not explaining a lot of variability in calories by knowing carbohydrate content because this seems to be a much weaker predictor of calorie count. However, if I combine these two pieces of information, I think we're going to have a lot more information to make a better prediction of calorie count. So we're going to visualize what happens if we do a multiple linear regression with just both of these predictors included. So I'm going to do this right here. How this code is set up, again, is really not important. I just want you to focus on the graph that we get. And, hold on. It takes a second. It shows up, and then it goes away, and then it shows up again. There it is. All right, so let's get this set up. So calorie count is going to be our y variable here. It's our response variable. And we're using sugar content and carbohydrate content to predict what calorie count could be. And you'll notice here that if I have both of these pieces of information, I'm actually getting a lot of good predictive power here in calorie count. So it's also colored, by the way, where the higher the color, I believe, let's see, I actually forget what color is representing here. Fat. So I forgot that I also included fat count as represented in color, but you can just ignore that for now. Focus on just the position of the dots here. So what's going on when we do multiple linear regression with two predictors is that we're really fitting a best fit plane. So instead of just a best fit line, which is what I'd have if I just had like one predictor, like if I just had this straight up scatter plot, I'd be fitting a line here. However, if I have two predictors, I really have a best fit plane here, kind of going through the data to say, given a carbohydrate content in one position or a sugar content in another position, my plane is kind of estimating where I think calorie count should be. And I'm also going to compare this here to what happens if I build a model with both of these predictors. I get an R squared of about 67%. So it's much, much better when I pull both of these variables together. So that's a quick summary of multiple linear regression. Especially at least if we have two, it's easy to visualize still. Once we get to 3 or more predictors, we can't exactly visualize what's going on, at least not not in the traditional way. I mean, I added a third variable with color, but the more predictors I add, the more dimensions are going on. And even though we can't visualize them, we understand the idea that I'm taking all this information and using that information to find a best estimate. That's still going to have some error, obviously. I'm still going to be off, but I'm going to have a much better prediction if I add good predictors to my model.